especially because the fourth person isn't like really in the crew first people.
All right, let's get started. So here's a hyperplane arrangement. We're living in R2. And remember, we were talking about finding out the number of regions of an arrangement. Okay? And today we're going to start, maybe even finish, proving this theorem of Zaslavsky that tells you how to do this combinatorially. So to do that, let me first define something for you. So let's say that you have the arrangement, and you pick one hyperplane. Okay, let's say that it's this blue one over here. We're going to call it H. Okay? And I'm going to use it to define two different arrangements. Okay? So the first arrangement, basically what I'm going to teach you is how to do deletion and contraction with hyperplane arrangements. So here's the arrangement. Here's the hyperplane I want to delete. And of course, the only natural thing is to delete it, right? So that's what you do. You just keep all the other hyperplanes. And you delete the blue one. This is called the deletion of H. And if you think about it for a little while, you're going to realize that the natural thing to do to define contraction is to look at the blue hyperplane. Okay. And then you're gonna just look at the intersections of this guy with the other hyperplanes. In other words, you're going to see what things are living on this blue hyperplane H. Here you see this point, and this point. So you get this point, and this point. Okay? This is called the contraction of H. So if I call these guys I, J, K, L, then these are still I, J, K, L. And then this guy, well, you see this, K became this guy, and L also became this guy. J became this guy, and I became this guy. Now, the point is that this is a hyperplane arrangement. So if this is a hyperplane arrangement in some field to the nth, in the n-dimensional vector space over a field, then this is also a hyperplane arrangement there. And now, I claim that this is also a hyperplane arrangement, even though maybe it doesn't look like hyperplane arrangement. But the thing you have to realize is that here we're living in a two-dimensional space, and the lines are one-dimensional. Here the blue thing is a one-dimensional space, and the points are zero-dimensional. So what we have here is a hyperplane arrangement inside H. H is one-dimensional, and the hyperplanes are zero-dimensional.
So it's really, you can think of it as a hyperplane arrangement in f to the n-1.
Right, and H is just some n-1 dimensional vector space. And so you're just going to think that it's a hyperplane arrangement. It just lives in one dimension lower. Okay. So this just consists of the hyperplanes in A such that they're not H. This is the deletion. And for the contraction, you consider for each, you consider the intersection of A prime and H for H prime in A such that H prime is not H.
So that's supposed to be commutative or whatever if you do it a couple times?
So is this commutative? I mean, remember deletion and contraction are...
But I mean, if you wanted to contract several guys, that's not totally obvious, is it? That's
Right, so Jameson's question is that for matroids, deletion and contraction were commutative, so you could delete and contract in any order. And the question is whether this is also true for arrangements. And it's almost true, but you have to be a little bit careful. And actually I want to avoid that topic altogether, and I'll be happy to discuss that with you guys. This almost behaves the same way as deletion and contraction, but it's a little bit different. And I'll be happy to explain this to you guys later if you want. But we're not going to use that. We're not going to need it. One reason to do this is this. So here you have an arrangement, and you have a hyperplane in the arrangement. So I claim that the number of regions of the arrangement A is equal to the number of regions of A delete H plus the number of regions of A contract H. And the number of bounded regions is the same thing. If H is not a coloop. 0 if H is a coloop. And so this is going to help us get a handle on these functions, the number of regions of an arrangement, the number of bounded regions of an arrangement. Okay. So proof. Just going to prove by picture. Just going to show you a picture, and you're going to see why this is true. We want the regions of this guy. Well, first, let's forget about the blue hyperplane. Let's forget about this guy. Okay. Well, this arrangement had a certain number of regions. So if you forget about the blue hyperplane, you had a certain number of regions. And now the question is, what happens when you add the blue hyperplane? Well, if you see, what happens when you add the blue hyperplane is that it's going to take this region and cut it in half. It's going to take this region and cut it in half. It's going to take this region and cut it in half. And it's going to take this region and cut it in half. So how many regions did H cut in half? Well, basically what you have to do is look at H. Okay, H looks like this, and each one of these segments where you cut a section in half is one of these segments. So you cut in half here because you have a region here. You cut in half here because you have a region here. You cut in half here because you have a region here. So the number of regions of this arrangement that the blue plane cuts in half is equal to the number of regions in the contraction. Okay. And that's basically the proof. That's basically the proof, and if you want to do this, it's the same thing. I'll leave it to you as an exercise, but it's really the same thing. Okay. Any questions about that? Region of A equals regions of A minus H plus regions of A contract H. And this is going to be basically the key ingredient of how we're going to translate our geometric question of regions into a combinatorial question about matroids. Because basically this is the one geometric argument that we're going to make. And make sure that you understand this one. Make sure that you understand this well. But this is the one geometric observation we have to make. And after that, it's just all going to be combinatorics. The point being that, remember, I want to show that the number of regions of A is given by the characteristic polynomial of the matroid. And so what I want to show is that the characteristic polynomial also behaves in this way, also satisfies an equation like this one. So maybe we should go back to let's say that you have a central arrangement. And remember that central means that all the planes go through the origin. Hyperplanes go through the origin. And again, what you showed in the first homework is that if you have a central arrangement, then that defines a matroid for you. And that matroid, there's different ways of describing it, but we said one easy way to describe it is that you just look at the normal vectors of the hyperplanes, and that's a vector arrangement. And so we just use the linear matroid on those vectors. Okay. From that matroid, we get a lattice of flats. And so remember that what we're after is the theorem of Soslavsky. That if you want the number of regions of the arrangement, you just go to the lattice and compute the characteristic polynomial at -1. And if you want the number of bounded regions, then you just compute the characteristic polynomial at 1. This is what we're after, that we can compute this geometric number combinatorially. And so what we're going to have to do for a little while is figure out the combinatorics of characteristic polynomials of lattices of flats. And that's the next thing we're going to do. And so again, to make sure we're on the same page, I'll just write the same example that we keep using. So we already computed the lattice of flats of this guy several times, right? Let's just forget about that loop. We said that the lattice of flats doesn't notice the loop. So 1, 2, 3, 4, 5. 1, 2. Am I doing this right? 1, 2. Yeah. 1, 3. 1, 4, 5. And then the other flat is 2, 3, 4, 5. Oh. So 1, 1, 3, 1, 4, 5, and now 2, 3, 4, 5, and now like this. There you go. One, 2, 3, 4, 5. And we know how to compute the Moebius function. You just start with a 1 here, and then at each point you look at the negative of the things below. You get -1, -1, -1. And here you get 1, 1, 1, 2. And here you get -2. Okay. So again, the idea is that the mu of the bottom should be 0, and if you add up mu of y for all the things y less than or equal to x, you should get 0. Sorry, so at the bottom the Moebius function is 1, and then at x is defined so that when you add up the numbers from the bottom to x, you get 0. We said this is how you define these Moebius numbers. But what I'm going to show you now is that, I mean, this lets you do this in practice. You can find these red numbers in practice. But I think you've noticed in the homework that this is kind of a difficult definition to work with if you don't really know what the Moebius function is. And if you want to find the Moebius number at 2, 3, 4, 5, maybe you don't want to have to go all the way to the bottom and compute everything all the way up. Maybe you want to just compute this number, and maybe you just want a formula for that number, mu of 2, 3, 4, 5, or mu of something. And so this is not possible in general, but in some cases it is. For example, you guys saw that in a Boolean lattice, you can find mu of something. In the division lattice, you can find mu of something. And we're going to see now that in any geometric lattice, there is a formula, which is not as nice as the ones we've seen so far, but it's a formula. So here's what it is. Let's say that you have a matroid, and you want the Moebius function of the lattice of flats. So it goes like this. If you want the Moebius function of a flat, hopefully we would get something like -1 to the something, but it's not so nice. What you get is this. You're going to look at all the sets whose closure is F. For example, if you're computing mu of 2, 3, 4, 5, then you want to make a list of all the sets whose closure is 2, 3, 4, 5. And then you're just going to say -1 to the number of elements of the set. So let's do an example. According to this formula, if you want to find mu of 1, 2, 3, 4, then, sorry, 1, 2, 3, 4 is not a flat, so you cannot find mu of 1, 2, 3, 4.
2, 3, 4, 5.
2, 3, 4, 5 is what I meant to say. Then you want to say, okay, what are the sets whose closure is 2, 3, 4, 5? Well, one of them is 2, 3, 4, 5, right? That's closed, so its closure is itself. But what else?
2, 3, 4.
2, 3, 4. 5 is in the closure of that. By the same reason, 2, 3, 5 would also work. Anything else? Whose closure is 2, 3, 4, 5?
I guess 2, 4, 5.
Not 4, 5, right?
No.
The closure of 4 and 5 is just 4 and 5.
Yeah.
But for example, 2 and 3
Yeah.
work because 4 is in the closure of 2 and 3. 4 doesn't add any rank to 2 and 3.
Right.
And in general, any two of these guys will work.
Right.
Yep.
So 2, 3 will work. 2, 4 will work. 2, 5 will work. 3, 4 will work. 3, 5 will work. And I think that's it. So hopefully this will work out. I didn't try to compute this ahead of time. But it says, okay, this guy gives me a +1. These guys give me +1s, +1, +1, +1, and +1. 1, 2, 3, 4, 5, 6. I have to find a mistake. Oh, there's more. There are more sets. Here we got 6 + 1s, right? I mean, for each one of these sets, you're going to say -1 to the number of elements of the set. So if the size of the set is even, it contributes a +1 to this sum. And if the set is odd, then it contributes a -1. So here we have 6 + 1s. And here we have 2 -1s. But I need to get 2. The idea is that if I take number of evens minus number of odds, I should get 2. So that means something's wrong.
Like 2, 4, 5, and 3, 4, 5.
And that means I'm missing 2 guys of size 3, hopefully, and actually I am. 2, 4, 5, and 3, 4, 5. Six minus 4 equals 2. Okay. So, of course, there's advantages and disadvantages to this. The disadvantage is that actually it was much faster to just work our way up to the poset. We were faster doing all of this than we were just finding this mu of 2, 3, 4, 5. So what's the advantage? One advantage is that this formula only depends on f. It's not a recursive formula.
Right.
It doesn't say, oh, you have to do everything below. So that's one advantage. And the other advantage is that actually, if your thing is monstrously huge, I mean, this is a small poset, and so it's easy to just work your way up. But if your poset is monstrously huge, then in some cases this is faster and easier to do than this. Okay, so this is what I'm going to show. So proof. Well, basically, if I want to show that this is the Moebius function, then what I need to show is that it satisfies these two conditions. So the first thing I need to show is that I'm claiming, maybe I should call this guy, let's call it nu of f. What I'm trying to show is that nu is equal to mu. So let's show that nu also satisfies these properties. So what's nu of the bottom element? It says you're supposed to sum over the things whose closure is the empty set minus 1 to the number of elements. Okay? But how many sets have closure equal to the empty set? Well, the only one is the empty set. So what I get is minus 1 to the size of the empty set, which is minus 1 to the 0, which is 1.
So you really are ignoring loops there, blatantly ignoring it. I mean, you were already, but...
Yeah, so maybe I should just say here loopless matroid.
That should be a mu there. That looks like a mu there.
So I'm just my plan is to show that this is mu, but I don't know that yet. So I'm calling it nu for now, and I'm going to show that nu satisfies these two properties, which is going to show that nu and mu are the same function. So the first property is satisfied. Nu of 0, nu of the bottom element is 1. And the second thing I have to show is that for x different from 0, the summation for y less than or equal to x of nu of y, that should equal 0. So what's this? This is summation for y less than or equal to x of nu of y, by definition, is summation over, I'm going to make the notation a little bit better. So let me call this guy f and this guy g. Or rather, this guy g. And so I'm adding over the things below it, nu of f. Because f and g are elements of the poset, so they're flats. And it's good if we call them f and g because that sounds like flats. So now summation for f less than or equal to g of nu of f. And by definition, nu of f is this summation. So I sum over the flats less than g, the sets whose closure is f. Okay. Well, so which x's am I summing over here? For each flat below g, I consider the x's whose closure is in g, is f. So in other words, what I'm doing is considering all the x's whose closure is less than or equal to g. Okay. But now, when is the closure of x less than or equal to g? Remember the order? The order in the lattice of flats is just containment. So I claim that when is the closure of a set inside G? I claim that that's equivalent to just saying that the set is contained in G.
Yeah.
So this is my lemma. Proof. Let's go that way. If the closure is contained in G, then X is contained in the closure. So X is in G. Okay. And to go back, if X is contained in G, then I can take closure of both sides. Closure of X less than or equal to closure of G, but closure of G is G. So I get the reverse implication. In other words, all I'm doing here is summing over the x is less than or equal to e of, no. I said closure of x less than or equal to g is equivalent to saying x is a subset of g.
Yeah.
So what I'm doing here is considering the subsets of g. Okay. And now, do you guys see why this is 0? That's what I have to show, right? I have to show that this summation is equal to 0. The reason this is 0 is that how many times? Let's just write it out. I get minus 1 to the size of the empty set plus
Something.
how many times am I going to get minus 1 to the things of size 1? I mean,
Order of G, choose order of, or choose 1.
I get a 0 when the chosen x is equal to 0. Plus, how many times do I get a minus 1 to the 1? Well, it's the number of one element subsets of G. G, choose 1. How many times am I going to get a 2? Minus 1 to the 2. Well, the number of times that I have a 2-element subset of G. G, choose 2. Dot, 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 dot. This is the same sum that we saw last time. This is just the binomial expansion of 1 plus minus 1 to the size of G. And now it's important to say that G is not the bottom element, so G is really a positive integer. And 0 to a positive integer is 0. That's it. So my function nu satisfies the recursive formula that I used to define mu, and that means that nu and mu are the same function. So now I have a formula for the Moebius function of a lattice of flats of a matroid. And the point is that now that's going to give me another formula for the characteristic polynomial. So remember, what is the characteristic polynomial? We said that this was just the summation where for each flat in the poset, you look at Moebius of the flat and q to the rank of the poset minus the rank of the flat. So, but instead of stating the theorem, I'm just going to prove it. And then you'll see what is the theorem that I want to state. This is the definition of the characteristic polynomial. And one thing that's a little bit tricky about this is that it involves these mu numbers, which were recursive, but now they're not recursive. Now we have a formula for them. So mu of f is that thing over there. Okay. Giving a lot of practice with these double summations where we keep doing the same thing every time. Write a big summation, invert the order of the summands. So now, what is it that I'm doing? First I sum over f, and then I sum over x. Well, let's just switch the summation. So for each x, now f is just going to be the closure of x. So that's just what I'm supposed to put here. And the only place where f is involved here is in this place, and f is the closure of x. So I get this.
So summing over all the f's in the lattice.
Can you just say R of X?
The point is, I mean, I'm skipping a step, but the thing is that it's kind of a silly step. When you flip the order of summation, now the first summation is over all the x's in E, and the second summation is over all the f's, such that f is equal to the closure of x. So really there's only one summand there. And now you get minus 1 to the x, q to the r minus the rank of f. And now I say, well, I'm only summing over the one f, which is the closure of x. So all I'm doing is computing minus 1 to the x times q to the r minus the rank of f is the closure of x. And so what I just proved is the theorem that if you want the characteristic polynomial of the lattice of flats of a matroid, then you just have to add up for all x's in E minus 1 to the x, q to the rank minus the rank of, what is the rank of the closure of x? It's just the rank of x. For M a matroid and L lattice of flats. Okay. This is known as Whitney's theorem. Okay. Okay, so we have a very messy board, and what are we supposed to make of this very messy board? The idea is this. Well, first I told you that we had a recursive definition of mu, but we wanted just a formula for mu of f that only depended on f. So that's what we got over there. Then here was my definition of the characteristic polynomial of a matroid, and we got used to that one. But the one thing that was a little awkward about it is that it involved these mu numbers that are kind of mysterious. So instead of having this expression, now we have an expression where there's no mu's. Okay? It's just something that depends on the rank function of the matroid, subsets of E. And so through some kind of trickery that we did here, we just got rid of the trouble of dealing with mu's, and now we have an expression for the characteristic polynomial that is much easier to work with. Okay. And these proofs, well, now you know they exist, but really what's more important is to realize that this formula exists. Now, maybe I should say, what is R here? R was the height of the lattice, which is the rank of the matroid. Okay. And now I'm almost ready to prove this. The point being that now I have a formula for this right-hand side that doesn't involve any mu numbers. But really, the next thing that I'm going to show you is this.
Federico,
Yeah?
Like n has to be loopless, right?
M is loopless. You might want to think about what happens if you have a loop here. You see that this formula, actually, so this is maybe a good exercise for you to think about. Exercise. If M has a loop, then what do you think? Then basically the summation is 0. So you just don't get the right thing.
Is that because our substitute, this thing only worked when M was loopless? Or is it because something else goes wrong as well?
Well,
You can trace it back to that.
Okay.
Yeah.
Then we could only do the substitution if we were on a loopless world.
And you'll see that if you try to substitute there on a loopless thing, you just get 0. Okay. So proposition. Let's say that you have a matroid. And you want the characteristic polynomial. You take an element. So the proposition is that if you want the characteristic polynomial of the matroid, then you can obtain it very, very easily from the deletion and the contraction. You just delete and contract.
can I ask a quick question about what you just said over here?
Mm-hmm.
Do you still get 0 if you have 2 loops? Or an even number of loops?
Yeah. You get 0 for the right-hand side. If you have any loops. And we're about to see a different proof of this. Because this is true for E not a loop, E not a coloop. If you happen to delete a coloop, then the formula is easier actually. It's just q minus 1 times this. And if you happen to delete a loop,
So in this case, M is not loopless.
so maybe the thing that I should say is just take M to be loopless. So this is just never going to happen. And this is what happens if for just about any element, if you want the characteristic polynomial of M, you just delete and contract. For a coloop, actually remember, or if you don't remember, then prove that for a coloop, the deletion and the contraction are isomorphic. And so if this were true, you would get the same thing minus the same thing. You would get 0. But for a coloop, you just get q minus 1 times the characteristic polynomial of either one of these guys. They're the same. It's called the deletion-contraction formula. So before I prove it again, let's think about what this is actually saying. Well, this is saying that now I have a third way to compute characteristic polynomials. So the first way was by computing these Moebius numbers recursively. So we saw that we could do that for small matroids. The second formula gives us an expression that does not involve the Moebius coefficients. And this third formula is the easiest of all, but it is recursive also. It tells you if you know how to compute the deletion and the contraction, then you know how to compute the matroid. So in a way, this is maybe the simplest one, but also the least revealing, because to do this, you really have to know how to do these two. Now, the point is that to do these two, you could just keep repeating this process, because for any matroid, you can just delete an element, contract an element. And so this is going to just make you do this. You take this one, and you delete, and you contract. Now you have to do this one, you delete, and you contract. You have to do this one, you delete, and you contract. So you just have to get this tree and just go down this tree and compute everything. Okay. Let's prove this formula. So to prove it, I'm going to use Whitney's theorem. Remember, Whitney's theorem is this one right here. So Whitney's theorem says just add up over all the subsets of E this expression over there. Now, let me split up the subsets of E into two groups, the ones that contain little e and the ones that don't contain little e. So the ones that don't contain it are these. And the ones that contain it. Notice that, not only notice, but make sure that you don't let me make a mistake here. When I write rank functions, I want to use the subscript m, because the reason being that I'm going to play with three different matrices here, m, the deletion, and the contraction. And so whenever I use ranks in this argument, I should put subscripts. Okay? Now, each one of these guys, I can write it as x equals y union e, because it contains little e. So instead of writing this as x, let me just write it as y union e, y union e. So x is equal to y union e, y is a subset of e minus e. Okay. Now, as you can imagine, the idea is that this is going to be the deletion. This is going to be the contraction. Why? Well, in the deletion, the rank of m is, just remember that the camera doesn't show this. So the rank in a deletion of a set is just the rank in the matroid. The rank of the matroid is equal to the rank of the deletion. Why is that? Because the matroid has certain bases. Now these guys, the bases are the ones that don't contain E. And there are bases that don't contain E, because E is not a coloop. I'm doing this for E not a coloop. So if E is not a coloop, then M and the deletion have the same rank. And so you see what I have here is exactly the summation over the ground set of M delete E of the same expression but for M delete E. So this is M delete E Q. For this guy, the rank, I mean, remember that the rank in the contraction of Y is equal to the rank in the matroid of Y union E minus the rank in the matroid of E. This is how rank works for contractions. And I leave this alone, and this is 1, because E is not a loop. That means that this expression rank in M of Y union E is equal to the rank in M contract E of Y plus 1. And the rank of a contraction is equal to the rank of M minus the rank of E, which is the rank of M minus 1. So that means that rank of M equals rank of the contraction plus 1. So this guy minus this guy, I'm going to cancel out the ones. And I'm going to get the same expression, Q to the rank of M contract E minus rank of M contract E of Y. And this is going to be the same expression of Whitney's theorem, except that I have this extra union E. And all that amounts to is that I have an extra factor of -1, which gives me a minus this big thing. So this guy is the characteristic polynomial of the deletion, and this guy is minus the characteristic polynomial of the contraction. So that's the proof. Now, if you want to do it for coloops, well, you just have to do the same thing and be careful about what happens with coloops. So again, another big proof involving lots of summations is